Hey everyone, welcome to this explainer. Today we're jumping straight into a mission to completely demystify a hidden invisible force. We are talking about the intense internal pressure that dictates whether the materials all around us are going to bend, stretch, or just completely break.
Have you ever wondered why a rubber band stretches so effortlessly, but if you drop a glass, it literally shatters into a million pieces? It's something we see every single day, right? But the answer takes us to the absolute limits of the physical materials in our world. To figure this out, we really need to uncover the relationship between two deeply connected, yet fundamentally different concepts: stress and strain.
Now, I know we throw around the words stress and strain interchangeably in everyday conversation, but in physics and engineering, they are entirely different beasts. Stress is the cause. It's the invisible internal resistive force acting as the instigator. Strain, on the flip side, is the effect. It's the measurable, totally visible physical consequence of that stress, the actual deformation of the material itself.
Okay, picture this. Think of a normal kitchen sponge being squeezed in your hand. That pressure from your fingers, that creates an internal force inside the sponge fighting back against your hand. That is the stress. You can't actually see it, but it's there. What you can see is the sponge squishing down and changing shape. That visible geometric change, that is the strain.
All right, let's break this all down. Section 1, the cause. We're going to look at the physical reality of how stress operates within a solid material.
It all really comes down to one brilliantly simple equation. Stress, which scientists write as the Greek letter sigma, is just F divided by A. That's the applied force divided by the cross-sectional area it's spread across. It's measured in pascals. Basically, this tells us stress depends entirely on two things: how much force you apply and the size of the area resisting it. If you double the force, you double the stress. But if you shrink the area that force is applied to, the stress completely skyrockets.
But, there isn't just one way to apply a force. We generally look at three primary types of stress based on how the load is applied. First up is tensile stress. Think of pulling a massive steel suspension bridge cable apart. It's a stretching force. Next is compressive stress. That happens when forces push inward, kind of like the crushing weight of a skyscraper pushing down on its concrete pillars. And finally, there's shear stress. This is a sliding parallel force, like the lateral shear acting on the metal rivets holding two steel plates together. Each type of external load creates a completely different internal stress pattern.
Let's put some real numbers to this just to see how wild it gets. Imagine a wire with a tiny cross-sectional area of just 0.0002 square meters. If you apply 500 newtons of force to it, which is roughly the weight of a person, you aren't just putting 500 newtons of stress on it. Because that area is so incredibly small, you are generating an absolutely mind-boggling 2.5 million pascals of internal stress inside that wire. A totally standard, relatable load creates massive, invisible internal pressure simply because of the geometry. So that's the invisible force. Now let's look at the visible consequence in Section 2, the effect, measuring strain.
The formula for strain, which gets the Greek letter epsilon, is simply the change in length, delta L, divided by the original length, L. But wait, do you notice what's missing there? There are absolutely no units. Unlike stress, which is measured in pascals, strain is a completely dimensionless quantity. It's literally just a ratio representing the percentage of deformation. Whether something stretches, compresses, or warps, strain just tells us how much its physical dimensions have changed relative to where they started. So, if a 100mm rubber band stretches by 5mm, the strain is 0.05. It's a 5% stretch.
To really get why this deformation happens, we've got to zoom way in. Section 3, the atomic springs and Young's modulus.
Think about the atomic level for a second. Imagine the atoms in a chunk of steel or rubber are hooked together by these tiny, invisible springs. That's what interatomic bonds act like. When you apply stress to a material, you are actually pulling against these atomic springs. Elastic strain, the kind of stretching that just snaps right back when you let go, is simply the temporary increase in the spacing between those atoms. The stiffness of those tiny springs dictates exactly how much the material will deform under a load.
So how on earth do we measure how stiff those microscopic springs are? Well, we use something called Young's modulus, usually just written as a big letter E. It's calculated by taking the applied stress and dividing it by the resulting strain. Because we are in the safe elastic region where stress and strain are directly proportional, Young's modulus becomes the ultimate ratio. It perfectly quantifies a material's overall stiffness. A super high Young's modulus means a very stiff material that heavily resists deformation.
When you actually lay out different materials side by side, the jump in these numbers is just staggering. Take rubber. It has a relatively low value, which is exactly why the weak bonds in polymers allow it to stretch so easily. But as we move down the list to wood, then aluminum, and steel, the numbers skyrocket. And look at diamond down there at the bottom. Diamond has an immense Young's modulus of 1.2 times 10 to the 12th pascals. Its atomic bonds are so incredibly strong, it takes a colossal amount of stress to produce even a tiny, microscopic fraction of strain.
Moving right along to Section 4. Let's map out this journey by looking at the life cycle of a material on the famous stress-strain curve.
You can literally think of this curve as the dramatic life cycle of a material being pushed to its absolute breaking point. Every material tested to destruction goes through these stages. First, we start in the elastic region, the safe zone. But if the stress keeps ramping up, we hit a critical threshold, the yield point. Beyond that, the material plunges into the plastic region, where permanent, irreversible damage happens. And if that invisible force continues its relentless assault, the whole thing ends in fracture, a catastrophic break. Let's step through this together.
First up, the elastic region. As we established, this is our safe zone. Here, stress and strain are perfectly directly proportional, creating a nice straight line on our graph. What's happening is our atomic springs are just being gently stretched. If you remove the load right now, the material will snap safely back to its exact original shape, just like a bouncy spring. No harm, no foul.
But watch out, because as that pressure builds, we hit a wall, the yield point. This is literally the point of no return. At this exact moment, the stress becomes just too much for the atomic springs to handle. The atomic planes inside the material actually begin to slip and slide past one another. We've left the safe zone and entered plastic deformation. If you remove the load now, it won't snap back. It's like bending a metal paperclip until it stays bent. Its shape is changed forever.
And if that stress just keeps coming as we move through the plastic region, we hit the ultimate climax, the fracture point. This is the catastrophic end of the line. The invisible internal stress finally overpowers the material's structural integrity entirely. Those atomic bonds separate completely, and the material physically violently breaks. Let's zoom back out from the microscopic world. Section 5, Real-World Engineering Applications.
Because, guys, this isn't just theoretical math. These concepts literally apply to your daily life. Engineers rely on this exact stress and strain data to select materials that keep us safe. A suspension bridge needs steel cables with an incredibly high Young's modulus, so they don't stretch too much under traffic. Safety helmets? They use polymers specifically designed to absorb impact energy through plastic strain without actually fracturing. And an aircraft fuselage requires materials that perfectly balance strength and flexibility to endure the massive stress of high-altitude pressurization.
But, real life is never just a simple math problem. As Dr. Audrey Zidonis expertly points out, effective material selection necessitates a comprehensive integration of dynamic environmental variables into the initial design cycle. Basically, the real world is messy. High temperatures can reduce a material's stiffness, flattening out that stress-strain curve. Even moisture can fundamentally alter something like nylon, giving it more strain but severely reducing its strength. Engineers have to account for the whole shebang to prevent disaster.
So, what's the big takeaway here? It's that our entire physical world is being held together by this invisible, microscopic tug-of-war. How stress causes material strain is absolutely crucial to everything around us. So the next time you drive across a massive suspension bridge, or even just stretch a rubber band in your office, will you feel those invisible atomic springs working beneath the surface? Will you picture the stress fighting to break the bonds and the strain visibly yielding to the force? It's an absolutely fascinating hidden physics that surrounds us every single day. Thanks for joining me on this explainer, and keep questioning the physical world around you.